Theorizing gravity and black holes. Hello, my name is Sophia Knowles, and I'm a 14-year-old GCSE student. I'm a space enthusiast and a member of the IOAA community. I hope to be able to research and study astrophysics and cosmology at a higher level in the future. Sources for this presentation are listed in the final slide. I'm passionate about this subject, and I really hope that you enjoy it and even learn something today. Isaac Newton. So I'm pretty sure we've all learned about Isaac Newton at one point, and he contributed greatly to physics. But it's also important to mention that before Newton, much of the foundations of Newton's laws of motion were based on Galileo's measurements and experiments. In 1687, Isaac Newton revolutionized physics when he published Principia Mathematica. In it, he provided a model for how gravity works. It's important to note that he did not state what gravity is. So Newton's first law of motion. Objects in motion will continue to move in a straight line, and objects at rest will remain at rest unless acted upon by an external force. A good example of this is when in sci-fi movies, say, two astronauts are being set off into space and they're traveling to Mars. They end up shutting off the engines once they are on course. This is because they will continue to move forward to Mars because there is no external force changing their path. And the only times they'll need to turn on their engines again would be to adjust the course or to land. So Newton's second law of motion is that net force is equal to mass times acceleration. This means that the velocity of an object changes when it experiences an external force. The more mass an object has, the higher the inertia. For example, a bowling ball would have more inertia than a volleyball because it has more mass. So it would require more external force to change its motion or state of rest. This describes how the acceleration of an object is equal to the force you apply to it divided by the mass. This means that things fall at the same rate in a gravitational field, since when you calculate the acceleration, the force and mass cancel each other out. Common sense, however, would tell you that a feather would fall slower than a hammer, but this is because of air resistance. In a vacuum, however, they would fall at the same rate because there is no air resistance. And we see this exact experiment being taken out on the moon, where an astronaut drops a hammer and a feather, and they do indeed fall at the same rate. Newton's third law of motion states that every action has an equal and opposite reaction. So Newton's law of universal gravitation. The gravitational force between two objects is proportional to the product of their masses and inversely proportional to the square of their distance apart. 50 years before this discovery, the astronomers Johannes Kepler came up with 3 laws that described the way orbits worked. We know that these laws were accurate because it matched what astronomers saw in the sky. Newton's law of gravitation was accurate to Kepler's laws, and combined with previous laws of motion and calculus, was able to prove them. So we see here that force equals gravity multiplied by the mass of one object times by the mass of the second objects divided by the distance between the center of those two objects squared. However, there was a problem. Due to Mercury's proximity to the Sun, it's difficult to see its transits. Transits being when a planet passes over its host star. However, when the planets would align in a certain way, scientists would gather to witness Mercury's transits. In order to predict when Mercury would pass the Sun, they would use Newton's law of gravitation. However, there was a problem. Mercury wouldn't appear on cue. This concerned scientists deeply, so they went searching for an answer to Mercury's lateness. They tried to explain this anomaly by suggesting that there was a planet that they hadn't discovered yet, which was messing with the orbits due to its gravity. They even said that the reason why they hadn't found it yet was because it was blocked out by the solar glare of the sun. They named this ghost-like planet Vulcan, but they couldn't find it simply because it didn't exist. Now that's where Einstein comes in. Albert Einstein, born in 1879 and died in 1955. Einstein was a theoretical physicist known for his development of the theory of relativity. It completely changed the way we viewed gravity, time, and the universe itself. But he had also a strong connection to politics. He was involved in anti-war demonstrations during the First World War. He was an advocate for civil disobedience. He warned of the dangers of nuclear war when there was a rise in anti-Semitism. Despite rejecting the idea of a biblical God, it led him to identify with the Jewish community since he was of Jewish descent. Einstein's efforts towards peace achieved little and certainly didn't achieve him much popularity, but he was offered the presidency of Israel due to his support of the Zionist cause. But he declined, saying that he was too naive for politics. But perhaps it's because, as he said, equations are more important to me because politics is for the present, but an equation lasts for an eternity. Theory of general relativity. In Einstein's theory of general relativity, he states that gravity is the effect of the curvature of space-time. Space-time is the fabric of the universe, where time is a fourth dimension. A good way to visualize this is to imagine a stretched out piece of fabric. That fabric is space-time. Now imagine if I place a bowling ball in the center, this for example would be the sun. It's a big and strong fabric. It will cause the fabric to dip and to curve. Then say we get some marbles and we set them in motion around the bowling ball, they will essentially start to orbit it. So when you are moving through a curved space-time, it appears that a force is acting upon you, which changes your path. Therefore, one of the first things Einstein did, using his geometric theory of gravity, was of course to calculate the straight line path of Mercury through a curved space-time. Fortunately, his calculations were exactly what had been observed on Mercury's transits. So why does everything fall at the same rate in a gravitational field? Because they are simply following the straight line path through a curved space-time. Another part of Einstein's theory is that energy is mass. We see this in his famous equation equals mc², which means energy is equal to mass times the speed of light squared. Therefore, light is the speed limit of the universe. You can't go faster than the speed of light. This is because if, for example, a spaceship tried to travel at the speed of light, as it approached the speed of light, its mass would become almost infinite. Time would nearly slow to a stop, and it would require an infinite amount of energy to push it to light speed. This is just impossible. To an observer, the spaceship would become increasingly squashed as its velocity came closer to the speed of light. This is not just an illusion in the frame of reference of the observer, but is exactly what is happening. Light always travels at 299,792,458 meters per second. However, its energy can change. For example, light would get shifted to the blue end of the spectrum as it gains energy and become shifted to the red end of the spectrum when it loses energy. That's because the more energy, the higher the frequency, therefore the more blue. The less energy, the lower the frequency, therefore more red. We know that light has no mass, so in Newton's theory, light shouldn't be affected by gravity, whereas in Einstein's theory, we know that light is affected by gravity. This is because it doesn't matter that light has no mass. It is following its path through a curved space-time. So, if an object has enough mass and curves space-time so much, it can cause light to bend around the object. This is known as gravitational lensing. It's important to remember that time is a fourth dimension, so when an object is heavy enough, it can warp space-time so much that it slows down time. This is known as time dilation. The twin paradox is a popular theme in sci-fi movies like Interstellar. But what is it? So, say we have two newborn twins. One is earthbound, let's call her Eve, and the other is sent to space traveling at a velocity of 80% the speed of light. Let's call her Lucy. When Lucy returns from her 8-light-year journey, it's Eve's 10th birthday. However, for Lucy, time has been ticking more slowly since she has been in a moving time frame. So by the time she comes back to Earth, it's only her 6th birthday. Eve, her twin, is now 4 years older than her. The universe is insane. From Lucy's perspective, she has been at a state of rest, and Eve is the one moving away from her. This paradox is solved by the fact that only Lucy has undergone acceleration. Lucy has been in 2 different time references, on the way into space and on the way back, whereas Eve has only been in one because she stayed on Earth. So, what is the evidence for general relativity? Initially, general relativity caused lots of controversy in the scientific community until, in 1919, Arthur Eddington provided the evidence needed to prove general relativity. Eddington traveled to the Atlantic of Principe to witness a solar eclipse and to observe the stars behind the sun. He photographed the stars that could now be seen due to the lack of solar glare. In the photograph, it showed that the positions of the stars had indeed been shifted due to gravitational lensing. To truly see the effects of general relativity at an extreme level, we need to see the most extreme thing known so far in the observed universe: black holes. So how do black holes form? Stars are fueled by something called nuclear fusion. Nuclear fusion is a process when hydrogen and helium nuclei are smashed together at high speeds and pressures. When hydrogen and helium runs out, the star will begin to die. The outcome of its death depends on how massive the star is. If the star is relatively small or average size like our Sun, so about 109 Earths across its space, and its diameter being 1.392 million kilometers with a circumference of 4,366,813 kilometers. At its main sequence, when its nuclear stores run out, it expands and becomes a red giant. It then shrinks into a white dwarf, then decays into a black dwarf. If a star is between 1.4 and 2.8 times the mass of the Sun, in its main sequence, it becomes a red supergiant star, then a supernova, then a neutron star. A neutron star has collapsed under its gravity to such an extent it consists almost entirely out of neutrons and it's extremely dense. If the star is more than 2.8 times the mass of the Sun, it will follow a similar route as to the neutron star, but instead will collapse into a black hole. This gravitational collapse happens because the mass of the star has been compressed into a volume called the Schwarzschild radius. I apologize for my pronunciation. What is the Schwarzschild radius? The Schwarzschild radius is the radius at which space-time surrounding a spherical mass becomes so curved it wraps around and encloses it. The Schwarzschild radius for the Sun would be 3 kilometers, and for the Earth, it would be 1 centimeter. So, to make the sun become a black hole, you would need to compress all of its mass into only 3 kilometers, and for the Earth, only 1 centimeter. However, it would be impossible to do that since there wouldn't be enough mass to allow for it. So a black hole is the most extreme object known to the universe. Nothing can escape it, not even light, the fastest thing in the universe. Due to the extreme mass of black holes, they warp space-time so much that time dilates to an extreme amount and light bends around it. Black holes are monsters that will suck up anything that gets too close. In a black hole, there is something called the event horizon. The event horizon is the point of no return. When something gets to the event horizon, it is impossible to escape. Nothing can overcome the gravitational pull. At the center of the black hole, there is a point of infinite density, yet infinite small size, according to general relativity. This is known as the singularity. We don't exactly know what a singularity is yet, but it's like trying to divide something by 0. So what if I pushed you into a black hole? So imagine we are 2 astronauts traveling near a black hole. We decided to both go out on a spacewalk. However, I am annoyed at you because you decided to eat the last Oreo. So logically, I decide to push you into the black hole. For fun, I decide to observe you falling into the black hole. I would see you fall into it slower and slower until you freeze. This is because black holes distort space-time so much, time slows at the event horizon. Due to the sheer amount of gravity acting upon the light you emit, the light becomes dimmer and redder due to losing its energy. So you would appear to become dimmer and redder until you just disappear. I would never see you fall in, simply because that light could never get to me, because even light can't escape a black hole. But from your perspective, you would fall into the black hole faster and faster. The light around you would be shifted due to the blue end of the spectrum because it's gaining energy. More gravity would be acting on your feet, which would stretch your body. This is known as spaghettification. I'm not kidding, scientists actually refer to it as spaghettification, because you are quite literally being stretched like a spaghetti string. You would become heavier and heavier. Then you'll be ripped apart atom by atom and die a very painful death. How lovely. So what is inside of a black hole? The short answer, we don't know. But there are many theories as to what could be on the inside of a black hole. Some people speculate, such as Stephen Hawking himself, that black holes could be a door to another universe. We know that there is a singularity located at the center of the black hole. Classical physics tells us that this is an infinite point of smallness and density, whereas quantum theory says that it is an extremely dense and small point, but it is not infinitely small and dense. As of right now, there is no way to know what is on the inside of a black hole, but there are some theories that are worthy contenders to find a solution to the problem. Hopefully, one day we will discover the answer to this. So, how do we even know that black holes exist if the light from a black hole can't even get to us? Well, in 2019, scientists across the world worked together to find a photo of a black hole. They worked on massive telescopes that collectively would add up to a huge telescope the size of the Earth itself. Luckily, when the photo was taken, the black hole was eating some light, so it bent around the black hole, thus illuminating it, so it allowed astronomers to take a photo of it. But before they took a photo of the black hole, how were they even sure they existed? When matter is dragged into a black hole, it will be heated up so much as it is ripped apart by gravitational forces, it would release X-rays into space. Scientists search for these X-ray signals and found a strong source in the Milky Way near a constellation called Cygnus. The orbit of this object, named Cygnus X1, was too massive to be a neutron star and was in fact a black hole. Black holes were no longer a theoretical entity. In fact, there is a supermassive black hole in the center of our galaxy. It is likely that it is common for galaxies to have black holes in the center of them, especially in spiral galaxies. But don't worry, we are safe. This black hole won't suck us into its gravity anytime soon. So can black holes die? If so, how, and how long would it take? That's when we meet Stephen Hawking. Stephen Hawking, born in 1942 and died in 2018. Stephen Hawking was a theoretical physicist and cosmologist. He was diagnosed with motor neuron disease, ALS, and he was given less than 2 years to live. The motor neuron disease slowly paralyzed him over the decades and meant that he had to use a speech-generating device to communicate. He greatly contributed to science, especially in the area of black holes, and sought for a unified theory of general relativity and quantum mechanics. It used to be thought that a black hole would never die until Stephen Hawking produced Hawking radiation. He said that black holes aren't completely black since they emit radiation. Quantum theory predicts that throughout space, pairs of virtual particles and their antiparticle appear to annihilate each other. Some of these antiparticle pairs will appear outside the event horizon of a black hole. It is possible that one of these particles will escape while the other falls into the black hole. To preserve the same amount of energy in the system, the particle that fell in must have negative energy. This would cause the black hole to slowly lose energy and mass. This is known as black hole evaporation. However, Hawking radiation is only a theoretical prediction. If it is correct, it would mean black holes do in fact die. But it would take up to a Google of years, which is a very long time, and we certainly won't be around to see it. In conclusion, we have learnt about Newton's theory of gravity, general relativity, and black holes. However, all of what I have touched upon today barely scratches the surface, so I hope it inspires you to learn more about it. I hope you have enjoyed today's presentation and that you have a nice day. And here is a list of the following resources used to make this presentation. Thank you for listening.